Correct. Determine the distance between consecutive antinodes. If the wavelength is 60 centimeter. Determine the distance between consecutive antinodes of a wave. If the wavelength is 60 centimeter. Determine the distance between successive antinodes of a wave. If the wavelength is 60 centimeter. Determine the distance between successive antinodes of a wave. If the wavelength is 60 centimeter. Determine the distance between successive antinodes of a wave. If the wavelength is 60 centimeter. Determine the distance between successive antinodes of a wave. If the wavelength is 60 what? Centimeter. Another question. A wave of frequency 10 Hertz forms a stationary wave pattern. Forms a stationary wave pattern in a medium. Forms a stationary wave pattern in a medium where the velocity is 20 centimeter per second. Find the distance between adjacent nodes. Find the distance between adjacent nodes. Find the distance between adjacent nodes. Class, we have two questions. The first question says, determine the distance between consecutive antinodes. If wavelength is 60 centimeter, they give option A, 15 centimeter, option B, 30 centimeter, option C, 60 centimeter, option D, 120 centimeter. Determine the distance between consecutive antinodes. If the wavelength is 60 centimeter, determine the distance between consecutive antinodes. Determine the distance between some consecutive antinodes. Class, what is the distance between consecutive antinodes? Is it not the wavelength divided by 2? So that will be 60 divided by, because consecutive antinode means an antinode and the next antinode after it. So 60 divided by 2 will give you what? 30 centimeters. 60 divided by 2 will give you what? 30 centimeters. That's for the first question. For the first. Now this question on the board now. A wave of frequency 10 Hertz, F is 10 Hertz, forms a stationary wave pattern. Plus, the stationary wave is one that produces antinode and nodes, remember. Where the velocity V is 20 centimeters per second, convert to meter per second, divided by 100. 20 divided by 100, you have 0.2 meter per. From centimeter to meter divided by 100. Find the distance between adjacent nodes, class. Let us first find the wavelength. On the wavelength, we can learn the distance between adjacent nodes. Wavelength is velocity divided by frequency. Class, wavelength is the velocity V divided by the frequency. Wavelength is the velocity V divided by the frequency. What's my V? My V is 0.2. What's my frequency? 10. So 0.2 divided by 10 will give you what? 0.02 meters. Well, my wavelength is 0.02 meters, but that's not what they asked me to find. They asked us to find distance between adjacent nodes. We know that distance between adjacent nodes means successive nodes. It's half of a wave. That's lambda divided by 2. Guys, I told you this, right? Node and a node, right? So wavelength divided by 2. What's our wavelength? 0.02 divided by, giving you 0.01 meter. So distance between adjacent nodes is 0.01 meters. Distance between adjacent node is 0.01 meter. Formula for wavelength in Wavelength is velocity all over frequency. It's still here, V over F. Wave speed all over frequency. Write down superposition. Superposition of waves. Super what? Superposition is the combination of two waves with different frequencies. While the interference is combination of two identical waves. Clear, difference between superposition and interference. Superposition is the combination of what? Two waves with different frequencies. Is the combination of two waves with different frequencies. Class, do not confuse superposition with interference, because you know why I mentioned interference, and I've taught it in the last class, right? The interference we have constructive and destructive, right? Class, difference between interference, because interference is something with combination of two waves. But why one is combination of two waves with different frequencies, this interference is combination of two waves with the same frequency. Just that the amplitude might be different. Maybe one has a higher amplitude than the other, but the same frequency. So like they say combination of two waves with similar frequency, your answer is interference. But in this question that you ask now, look at, they say the combination of sound waves with different frequencies is known as A, interference, B, diffraction, C, superposition, D, resonance. The answer is superposition. Super what? Position. Look at this question. The colors seen in the thin films of oil on the road and in soap bubbles are due to. There's some questions that you will know. You wonder where will I read this kind of thing in Facebook, but they're asking it in Jamb. This is a Jamb question. The colors seen in the thin films. I wish just that I recommended this book. This book, as it treats each topic, then brings all Jamb passion on that topic. Go to the next topic, then all Jamb passion on that. So like I'm on wave now, I have several questions I can ask you. You see, I was scrolling through several wave questions. When I go to electricity, several questions, and they are all Jamb standard questions. Do you understand? Now look at this one now. So it gives you things that even the test did not mention when teaching the wave, but it's in the Jamb. The book with science physics. I don't know if you know the book. Afolabi. Have you heard of this Afolabi physics? It was time it was strange. It's very, it's no longer I had it. If you ask for Afolabi physics, you know, in the West they are very good in education. Very good. It's the best people, the best academics. Like if you know that this year, but we're even joking here. To get medicine in school like UI, you know it's harder than Uniport. The standard. First of all, they will check your WAEC first. So the standard of education, that's where education started from in the whole Nigeria. So the first university in Nigeria was University of Ibadan, UI, Premier University. Then you have OAU before you now start bringing to this south side. South side people were the last people to accept education. They prefer their farming, their fish, they have rivers, now waterline, riverine environments. So this Afolabi physics is very, very good. Just that I don't know, if you check all this, ask them Afolabi physics. Each topic from chapter 1, measurement units, all questions on measurement units is there. Different Jamb questions. So as you're studying, you are seeing access to Jamb questions already. Eh? All what? Yes, all inclusive, yes. All Jamb, this will cover everything in Jamb. It's what I've been using to teach Jamb for a long time. But if I'm thinking of questions, instead of going to Jamb pass, if I will start tracing the question, this one helps me now. I was even looking for the book, or this why. Yesterday I just check, and I saw it. I said yes. Or if I teach any topic and I want to bring enough examples, I have enough. Over 50, 100 different. I tell you the year it came out. Not that it will just be giving you questions. Tell you the year, you can go and check it. Tell you the exact year it came out, the question number of the year it came out. So you can go and say, okay, so these people actually went to go and sit down and trace out all questions on waves. When you go to electricity, trace out all questions on electricity. When it goes to magnetism, all Jamb questions on magnetism. And they will solve it with solutions like that, step by. So as we have finished that topic, you can take question on that. I'll see if I can change it to PDF and send to the group. So you can also have it. I'll see if I can convert to PDF and send to the group. What I'll just do is snap it and use scanner and scan. It will take time, but I'll try. Someone should just remember, I'll try. So you can also use it for your personal studies. Very good book. For me to hold, I don't like holding books when teaching, but for me to hold this book, that it's strong. Strong. It's a very strong book. And it has examples. So sometimes you can teach finish, you can't start forming an example in your head. You need something that will be giving you direction, so you'll be faster. You will start thinking of an example. If you have taught wave now, nothing. What person will I give them an example? This one has already brought it out. Jamb has brought it out already for you, Jamb. Several questions. So, yes. Now moving forward. What was a superposition? Yes. I was about asking a question, right? Where is that in? Yes, look at this now. We can say you are finished with, but you can not see this now. The colors seen in the thin films of oil on the road and in soap bubbles are due to the colors seen in thin films of oil on the road and in soap bubbles are due to A, reflection. B, interference. C, diffraction. D, polarization. This is why I can't think I said that. There are some things that no matter even if you cover your scheme of all, there are some Jamb questions you cannot still answer until you practice Jamb questions. Because you just find out where should you have read this? Wait, tell me the topic. You have to wave now. Where is there when they say color bubbles stuff? I'm fast. Okay, I'm fast. Am I fast, class? You just started as I said, nobody's saying I'm fast. I'm not fast. There are too many things to cover, but I will slow down. I'll slow down a bit. Am I slow now? My name is Success. Should I slow? My name is... I'm on record, let me not joke too much. I just guess. Who has good guessing power here? You guessing used to favor you. Eh? And I repeat the question. The colors seen in the thin films of oil on the road and in soap bubbles are due to correct interference. You guessed? You've seen it before. Good. You see? That's the answer. You've seen it before. So I feel that this guy, you have seen it before, and I didn't know this is my book. This guy he will bring out all the Jamb past question on that topic. I will try and scan this thing and send to you guys. Especially for physics. If you use this thing, I will scan it and do it as PDF, send to our paid members group. I will not send to general group also. It's not for everybody. Because this thing to scan it is stressful. Okay, look at this question. Two identical waves traveling in the same direction. There are some things that I can only show you with question. There's no way to teach it. It's just to show you. When I say question, I'll remember and tell you. Look at this. Two identical waves traveling in the same direction are superimposed. Now what? What should be the phase difference between the waves for maximum destructive interference to occur? What should be the phase difference between the waves for maximum destructive interference to occur? This kind of question, never forget their answer because they're just one. That's how they will ask them. They will not change it. Two identical waves traveling in the same direction are superimposed. Two identical waves traveling in the same direction are imposed. What should be the phase difference between the waves for maximum destructive interference to occur? A, 20 degrees. There's no calculation, it's just a fixed answer. So there's no formula, you just know it or you don't know it. What should be the phase difference for maximum destructive interference to occur? One eight, correct. How are you getting these things? But you guess this one, don't lie. You guess this one, are you? This was as 19. This guy goes back as far as 1997. 1997 Jamb. Question 32. Question 32. You see how far back. That's why he has a lot of Jamb questions. This is 1997 Jamb. Even as 1995, he has 2003 or more. So this is 2021, number 3. There's nothing in physics that is not here. Which of the following properties are common to all waves? Which of the following properties are common to what? All waves. I, diffraction. II, refraction. III, interference. A, I only. I what? B, I only. C, I and I only. D, I and I. Which of the following properties are common to all waves? Which of the following properties are common to what? All waves. What's the answer, class? D. This is correct, class. Do you know what they were put here that you say is not common to all waves? There's only one property that is not common to all waves, polarization. When looking at general characteristics of waves, polarization is not common to all waves. Polarization is specific to light waves only. Light. Because actually, when we're listing properties or general characteristics of waves, we have reflection, we have refraction, we have diffraction, interference. One last one is polarization. But polarization is only peculiar to light waves. It's what we call plane polarized light. When light waves pass through a plane polarized light, it has the ability to rotate that plane polarized light in a particular direction. So polarization is one. Note, you can ask it another way. If you saw polarization, then remove it. Polarization is not popular to all waves. A parallel beam of unpolarized light. Write down. A parallel beam of unpolarized light. This came out 2006 Jamb on question 9. 2006 Jamb question 9. A parallel beam of unpolarized light is incident on a plain glass surface at an angle of 58 degrees. A parallel beam of unpolarized light is incident. A parallel beam of unpolarized light is incident on a plain glass surface at an angle of 58 degrees. On a plain glass surface at an angle of 58 degrees to the normal. At an angle of 58 degrees to the... If the refracted beam is completely polarized, if the refracted beam is completely what? Polarized. Calculate the refractive index of the glass. If the refracted beam is completely polarized, calculate the refractive index of glass. Any question we saw, please don't forget the formula that was used. I am picking them for a reason. They are not popular things you will know or you read up on your own. Guys, do you know it's what we call Brewster's law of polarization? Brewster's law is the formula we are going to use. Calculate the refractive index of the glass. Calculate the refractive index of the glass. We said a parallel beam, let me come again. A parallel beam of unpolarized light is incident on a plain glass surface. Is incident on a plain glass surface at an angle of 58 degrees to the normal. At an angle of 58 degrees to the what? If the refractive beam is completely polarized, calculate the refractive index of the glass. Class. N, according to Brewster's law, the refractive index N equals to tan theta. Tan what? Theta. Where theta represents the angle of incidence. Where theta represents the angle of what? Incidence. Where theta represents the angle of what? Incidence. N equals to tan theta. And the angle of incidence is 58 degrees, class. So that will be N equals to tan 58. This kind of question, if you don't know, you don't know it. And tan 58 degrees is 1.600. Eh? N is equal to tan theta. Theta is angle of incidence. Theta represents angle of what? Theta represents the angle of incidence. Angle of what? NC. Theta represents the angle of incidence. A narrow beam of unpolarized light of intensity 10.2. A narrow beam of unpolarized light. A narrow beam of unpolarized light of intensity 10.2 is incident at an angle of 30 degrees to the axis of the Polaroid. A narrow beam of unpolarized light. A narrow beam of unpolarized light. A narrow beam of unpolarized light of intensity 10.2 is incident at an angle of 30 degrees. Is incident at an angle of 30 degrees to the axis of the Polaroid. To the axis of the Polaroid. What is the intensity for the emergent polarized light? What is the intensity for the emergent polarized light? What is the intensity for the emergent polarized light? I equals to I naught cos squared theta. This is Malus law. I equals to I naught cos squared theta, where I naught represents the what? The reference intensity which they've given us. That's 10.2. They say what is the intensity for the emergent polarized light? We're looking for I. Plus I naught has been given already. 10.2. Intensity can be measured in decibels. Can also be measured in webers per meter square. Webers per meter. WB per meter square. Decibels or webers per meter square. Class, so theta, they give us theta in the question to 30 degrees, yes, 30. So I'm going to say I know which is 10.2 cos square 30 degree. 10.2 cos square 30 degree means cos 30 degree all square. Cos square 30 degree means cos 30 degree all. That's 10.2. Cos 30 degree is 0.866 all. So 10.2 times 0.86 is all square. Do we have 7.65? Someone should confirm. 10.2 times what? Times 0.86 is all square. You don't know, people don't have calculator. Okay, Jamb does not allow scientific calculator, shit. Are they still allowing? They don't allow. They have their own calculator in the system now. Okay, 7.649, which is 7.65, which is 7.65. I think you get this one. I don't need to write down. Listen. In a wave, the maximum displacement of particles from their equilibrium position is called. In a wave, the maximum displacement of a particle from their equilibrium position is called A, frequency, B, amplitude, C, period, D, wavelength, E, wave velocity. What's the answer? Amplitude. The change in direction of a wave front. Follow me. You have to get ready. Jamb, there are a lot of Jamb questions, and only 40 will come out. Take as many Jamb questions, you'll never forget the answers as much as possible. The change in direction of a wave front because of the change in velocity of the wave in another medium is called class. In another medium, once a year in another medium, just know it's refraction. In all waves, it's only refraction that waves move from one medium to another. Because class, everything about the wave will change. I told you that the velocity of the wave will change. The only one thing will not change. Remember, what's that thing? Frequency of the wave does not change. I've said it before, right? Frequency of the wave does not. So the change in direction of the wave, direction will change. The change in direction of the wave front because of the change in velocity of the wave in another medium is called refraction. Refraction. Which of the following is not a property of longitudinal waves? Which of the following is not a property of longitudinal waves? A, compression. B, reflection. C, refraction. D, polarization. E, diffraction. Which is the property? Compression. No, it's this. It's polarization. It's what? Because longitudinal waves are sound. Longitudinal waves are what? Why did I not tell you that polarization is really peculiar to light waves? Polarization is really peculiar to what? So, longitudinal wave will not undergo, they don't undergo polarization. So the answer is polarization is really peculiar to what? To light waves. Look at the acid again here. Longitudinal waves cannot be A, diffracted, B, refracted, C, polarized, D, reflected, E, superposed, is polarized. Longitudinal waves cannot be polarized. Let's now go to sound waves. Let's go to sound waves. So write down production and propagation of sound waves. Production and propagation of sound. Another reason why I like this book is that it gives you what you need to read. So you know that sometimes if you read it, the thing will be so bored, so many stories, and you don't have time. This one gives you in points. You know, when you're preparing for exam like this, you need a textbook that's giving you the things in key. Boss, give me the points, the key things. Sound waves, production and propagation of sound waves. Production and propagation of sound waves. Production and propagation of sound. Let's note the few key points about sound waves first. One, let's note the few key points about sound wave. One, sound wave is a mechanical wave. Sound wave is a mechanical wave as it requires a medium, such as solid, liquid, and gas. Sound wave is a mechanical wave as it requires a what? Medium. Our topic is production and propagation of sound waves. Production and propagation of sound. Production and what? Propagation of sound waves. Sound wave is a mechanical wave. Number one. Sound wave is a mechanical wave as it requires a medium. Such as solid, liquid, and gas. Class. Any wave that cannot travel through a vacuum without a medium is not a mechanical wave. So it's a mechanical wave. So we say it requires a medium such as solid, liquid, and gas for its propagation. It requires a medium such as solid, liquid, and gas. Two, it is a longitudinal wave. So one, sound wave is a mechanical wave. It's giving you the key points, for example. Someone can actually explain it's not a mechanical wave. Two, it's giving you key examples about everything that you need to know about sound wave, for example. Not wasting your time. If you open some other text, what they will first do about sound, then you're wasting time. Two, is a longitudinal wave. Is a longitudinal wave. Three, another key points. Three, the velocity depends on temperature, wind, density, and elasticity of the medium. Three, the velocity depends on temperature, wind, density, and elasticity of the medium. The velocity of sound depends on. This is a key example, and this way they can use this in the exam, which you're following does not, the velocity of sound not depend on. So it depends on temperature. You see temperature. So you must first know the one it depends on before you know the one that is not dependent on. Wind depends on temperature, wind, density, and elasticity of the medium, elasticity of the class. Velocity of sound depends on temperature, wind, density, and elasticity of the what? Medium. Note that it does not is independent of the pressure. Velocity of sound is independent of the what? Pressure. Exam point. Which of the following does velocity of sound not depend? Answer is what? Pressure. Velocity of sound is independent of pressure. Class, take note. Velocity of sound is independent of pressure. So class, how fast the sound wave will move does not depend on the pressure applied. Velocity of sound is independent of pressure. Velocity of sound is independent of pressure. Another property of sound is that it exhibits Doppler effect. It exhibits what? Let's define Doppler effect. It exhibits Doppler. Sound exhibits Doppler. So let us define Doppler effects. Doppler effect is the apparent change in the frequency of sound. It exhibits Doppler effect. Is on the board. Doppler effect, let's define Doppler effect. You could be asked in the exam. That is the apparent change in answer, Doppler effect. Doppler effect is the apparent change in the frequency of sound due to relative motion. Doppler effect is the apparent change in the frequency of sound due to relative motion between a source of sound and an observer. Due to relative motion between a source of sound and an observer. Due to relative motion between a source of sound and an observer. Doppler effect is the apparent change in the frequency of sound. Doppler effect is the apparent change in the frequency of sound due to relative motion between a source of sound and an observer. Due to relative motion between a source of sound and an observer. Class, it has a formula. Doppler effect has a... I'll come again. Doppler effect is the apparent change in frequency of sound due to relative motion between a source of sound and an observer. This can be well explained if you're in a car and it's moving and they're playing music somewhere. As they're going away from the music, the frequency of the sound is reducing. Apparent change in frequency of sound because there is not relative motion between the observer and the source of the sound. You experience Doppler effect. Formula for Doppler effect: F prime equal to F into bracket V plus V naught all over V minus V naught. Class, we have two formulas. When the observer is approaching, when what? You can experience Doppler effect when you are approaching, getting closer. Maybe there's a plane in sound somewhere, it's getting closer, approaching, or when you are receding. When you are receding, the formula is F prime equals F into bracket V minus V naught all over V minus Vs. This one is when receding. The opposite of approach is to recede. Receding. Class, in this formula, F prime means the new frequency. F prime means the what? Remember that it's the apparent change in frequency of sound. So there's a new frequency. F prime here means the new. You usually have to calculate the new frequency of sound. And the normal F, if you notice the formula, there's F prime and there's normal F, right? The normal F represents the initial or true frequency, the initial or true frequency. V, if you look at the formula, there's normal V. V represents the speed of sound in air, speed of sound in. And you also see V naught there, right? V naught represents the speed of the moving observer, speed of the moving observer. Speed of the what? V naught represents speed of the moving observer, and Vs represents speed of the moving source. 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 Vs represents speed of moving source. Let's take a question for that part. An automobile moving at 30 meters per second. An automobile moving at 30 meters per second is approaching a factory whistle. An automobile moving at 30 meters per second is approaching a factory whistle. An automobile moving at 30 meters per second is approaching a factory whistle. Whistle, W-H-I-S-T-L. W-H-I-S-T-L-E. Whistle. An automobile moving at 30 meters per second is approaching a factory whistle. Class, what is the price of them telling you approaching? So you know the formula to use. If they say it's going away from, you use the second one, receding. But this one is it's approaching a factory whistle that has a frequency of 500 hertz. That has a frequency of 500 hertz. So it means that the true frequency is 500 hertz. That has a frequency of 500 hertz. If the speed of sound in air is 340, V If the speed of sound in air is 340 meters per second, class, speed of sound in air is 340 meters per second. If the speed of sound in air is 340 meters per if the speed of sound in air is 340 meters per second, what is the apparent frequency of the whistle as heard by the driver? What's the apparent frequency of the whistle as heard by the driver? What's the apparent frequency of the whistle as heard by the driver? Class, V naught is speed of moving observer. Who is moving observer? The automobile. And the automobile moving at 30 meters per second. So the observer is moving at 30 meters per. Now, Vs is speed of the moving source. Class, when the source is not moving, you take it as 0. For example, in this question, we are not told that the source is moving. Class, the source means the sound source. Remember that it's the source producing the sound, right? Vs is the speed of the moving source. But in this question, the source is not moving, so it's 0. Nobody will tell you that it's 0. As long as you look at the question, you see that the source was not said to be moving, is what? 0. But V naught is speed of the moving observer, 30 meters per hour. Then V, normal V is speed of sound in air. Normal V is speed of sound in air, which is 340. And F is frequency. You can use all these formulas to attain the what? Frequency, F prime. We're looking for F prime when approaching. So my F prime, applying the formula with F500, F5 into bracket, who is V? 340 plus who is V naught? 30 all over who is V again? 340 minus who is Vs? V naught, sorry, V naught is 30. 340 minus 30. Here, okay, V plus V naught, V minus V naught. So 340 plus 30, 340 minus 30. I'm going to need Vs for this. Did I give you Vs in that formula? Did I give you a wrong formula? Let me see. Apply effect, where are you? Class, what is this formula I give you for approaching? Yeah. Well, this will be S, V minus Vs. V minus what? F into bracket V plus V naught all over V minus Vs. And F into bracket V minus V naught all over V minus Vs, correct, yes. When is receding, F into bracket V minus V naught all over V minus Vs. When is approaching, F into bracket V plus V naught all over V minus Vs. Yes, so who is Vs? 0. So 340 minus 0. But this one is V plus V naught, 340 plus 30. So that will be 500 into bracket 340 plus 30, 37. All over 340 minus 0, 3. So about 500 times 370 divided by 340. I think you have 544 hertz. Can confirm. 544 what? Hertz. After doing the math, I'll give you another question just to be sure that we are good in this area. Are we ready? A car moving at 20 meters per second with its horn blowing. A car moving at 20 meters per second with its horn blowing. A car moving at 20 meters per second with its horn. Horn is H-O-R-N. With its horn blowing. A car moving at 20 meters per second with its horn what? Blowing. Open bracket. After putting on blowing, open bracket. F equals to 1,200 hertz. F equals to 1,200 hertz. It's chasing another car going at 15 meters per second. It's chasing another car. It's chasing another car going at 15 meters per. It's chasing another car going at what? 15 meters per second. It's chasing another car going at 15 meters per second. What is the apparent frequency of the horn as heard by the driver being chased? What is the apparent frequency of the horn as heard by the driver being chased? What is the apparent frequency of the horn as heard by the driver being chased? What is the apparent frequency of the horn as heard by the driver being chased? What is the apparent frequency of the horn as heard by the driver being chased? What's the apparent frequency of the what? Of the horn as heard by the driver being what? Chased. Take the speed of sound as 340 meters per second as heard by the driver being chased. What's the apparent frequency? I'll come again. What's the apparent frequency of the horn as heard by the driver being what? Chased. Take the speed of sound as 340 meters per second. Take the speed of sound as what? 340 meters per. Take the speed of sound as 340 meters per seconds. Class, let's do this together. A car moving at 20 meters per second with its horn blowing means that that car that is moving is the source of sound. It's the one playing horning. Which is on what? So it's the source of. So speed of moving source is Vs, is 20 meters per. A car moving at 20 meters per second with its horn blowing. So the car is moving, so the moving source. The car is the source and it is moving with 20 meters per. So speed of moving source is 20 meters per second. Class, the true frequency is what? F, 1200 Hertz. Chasing another car at 15 meters per second. The second car is the observer. V0, 15 meters per seconds. What is the apparent frequency of the horn as heard by the driver being chased? So the driver being chased is the observer. Take speed of sound V, normal V now is 340. This is a constant, whether they give you or not. Speed of sound in air is a constant 340. Just like speed of light is 3 times 10 raised by 8 meters per second. Speed of light is a constant, also speed of sound is also a constant. Now, it's very related to solve. When they say chasing, know that it's receding. Anytime you hear chasing under Doppler effect, know that it's what? Receding, second formula. So, you not use the one for approaching, you use the one for what? Receding. Use the second formula. Anytime you hear chasing, it means receding. Class, the apparent frequency is what we're looking for. Is F, what is 1200 into bracket? Who is V? 340 minus, who is V naught? 15. All over V again, 340 minus, who is Vs? 20. So you have 1200 into bracket, 340 minus 15. All over 340 minus 20. Do the math, do the math, do the math. You should arrive at 1220 Hertz. 1220. 1220 what? Hertz. Types of sound, subheading, types of sound, subheading, types of what? Sound, subheading, types of sound, subheading, types of sound. This is any part you are not understanding. This session is being recorded. I always post it. You can notice every night or later the next morning I'll post it, right? You can calm yourself down and watch it again. You can even use one, you're just writing out the notes or add the notes, but you go and watch it. You're now using the video to be collecting, well, this is why I wrote, okay. Watch it again, watch it several times and know it. Show this aspect. Types of sound. One, we have fundamental. Fundamental is sound of the strongest single and audible frequencies. Fundamental sound. Fundamental is sound of what? Strongest single and audible frequency. Fundamentals. Types of sound. Fundamental. Types of sound. Like someone that is watching the video can replay it again, pause it and assimilate. Fundamental. Sound of the strongest single and audible frequency. An audible what? Frequency. We have octave. Octave. Octave is sound of twice the fundamental frequency. So twice of this is octave. Sound of twice the fundamental. Sound of what? Sound of twice the fundamental. So why fundamental frequency is the sound of the strongest single and audible frequency? Fundamental frequency is the sound of the strongest single and audible frequency. Obtain the sound of twice the fundamental. We have harmonics. Harmonics is the sound of multiples of the fundamental frequency. Sound of multiple of the fundamental frequency. Sound of multiple of the fundamental frequency. Sound of multiple of the what? Fundamental frequency. So harmonic, you can say second harmonic. If someone says she finds second harmonic, it means twice the fundamental frequency. Second harmonic means what? H2, which is 2 of the fundamental frequency. We usually use F naught to represent fundamental frequency. F naught, fundamental what? Second harmonic. If you say fourth harmonic, it's 4F naught. So harmonic is just a sound of multiple of the fundamental what? Frequency. We have overtone. Overtone. Overtone is sound of frequency above. Overtone is sound of frequency above. Overtone is sound of frequency above and multiple of the fundamental. Sound of frequency above and multiple of the fundamental. Sound of frequency above and multiple of the fundamental. Sound of frequency above and multiple of the fundamental. Ultrasonic. Now we're looking at types of sound. Ultrasonic. Ultrasonic. Ultrasonic is sound of frequency above the hearing range. Plus, ultrasonic is sound of frequency above the hearing range. It's called sound of frequency above the hearing range. That is sound of frequency above 2000 hertz. That is sound of frequency above 2000 hertz. Beats is also a type of sound. Beats. B-E-A-T. B-E-A-T. Beats. Beats. B-E what? A-T. Beats. Beats is a throbbing sound produced. Throbbing sound produced. Throbbing sound produced. When two sounds of nearly equal frequency are combined to give a single common frequency. Throbbing sound produced when two sounds of nearly equal of what? Nearly equal frequency are combined to give a single common frequency. Are combined to give a single common frequency. Are combined to give a single common frequency. When two sounds of nearly equal frequency are combined to produce a single common frequency. Echo. Echo is another type of sound. Echo. Echo. Echo is sound produced after the reflection of sound wave. Echo is the sound produced after the reflection of sound. Sound produced after the reflection of sound wave. Just like light waves can be reflected, sound waves can also be reflected. You say, mention a sound and you're not hearing your voice back. Don't know that sound has been reflected back to you. Remember, the reflection is sending back of wave from where it came. After hitting an obstacle, it comes back. It's reflection. So if you say something and then you are hearing that thing back, it means that that thing you said has hit and sent back to you. Reflection of sound, produce sound produced after reflection of sound waves. Echo is sound produced. Note, for an echo to be distinct from the original sound. Note, for an echo to be distinct from the original sound. Note, for an echo to be distinct from the original sound. Note, for an echo to be distinct from the original sound. For an echo to be distinct from the original sound. For an echo to be distinct from the original sound. There must be a minimum time interval of 0.1 seconds. There must be a minimum time interval of 0.1 seconds. There must be a minimum time interval of what? 0.1 seconds. A minimum distance of 17 meters. 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 Or the reflected wave must have traveled a total distance of at least 3 meters. Or the reflected wave must have traveled a total distance of 33 meters. Or the reflected wave must have traveled a total distance of 33 meters. Or the reflected wave must have traveled a total distance of 33 meters. Or the reflected wave must have traveled a total distance of what? 33 meters. Let's look at echelon. This echo or sound head when the pavement near a fence is the echo or sound head. Echo or sound head when echo or sound head when the pavement near a fence. When the pavement near a what? Fence made of equally spaced iron bars. Made of equally spaced iron bars. Equally spaced iron bars. Made of equally spaced iron bars or any series of regularly spaced reflecting surfaces, or any series of regularly spaced reflecting surfaces. Let's look at reverberation. Reverberation. Reverberation is also known as indistinct echo. Indistinct echo. Reverberation. Reverberation. I hope you have the spelling correct. Reverberation. R-E-V-E-R-B-E-R-A-T-I-O-N. Reverberation. R-E-V-E-R-B-E-R-A-T-I-O. Reverberation is also known as indistinct echo. or sound that cannot be distinguished from the original sound, or sound that cannot be distinguished from the original, or sound that cannot be distinguished from the original sound, or sound that cannot be what? Distinguished from the original sound, or sound that cannot be distinguished from the original sound. When we come in our next class, we'll continue from here. We'll continue from